Okay, so here we're going to be looking at transformations with two new types of parent functions. Both parent functions are radical functions. The first one is the square root function, which is essentially the square root of x as the parent function. You can see it starts at 0, 0, and then curves off to the side. Each of the reference points we have here and that we'll be using to help us graph are basically a perfect square, comma its square root, because the y value is found by just square rooting x. And the second one is another radical function that is the cube root of x. And the order pairs we're going to be using to help us graph, the reference points are -1, -1, 0, 0, and 1, 1. Those reference points, again, are just found by cube rooting each of the x values. Usually when we use the reference points, we use -1, 0, and 1. We can't use -1 for the square root function because you can't square root -1. It's imaginary, but here we can. So if we want to get a third point to help us with the shape, we use 4 because it's the next perfect square for the square root function. Okay, in this example, we are asked to state the domain and range of the function f of x equals -2 square roots of x plus 1, and then plus 3 on the outside. There's a couple of different approaches we can take, but since our goal is to explore transformations, we're going to be doing it with transformations. If we know the original parent function is the square root of x, its graph looks something like that. I can tell its original domain starts at 0 and goes to the right all the way to positive infinity. So the original parent function's domain is x greater than or equal to 0. Similarly for the range it starts right here at the y value of 0 and goes upwards, which means we can have the output values starting at 0 and going upwards. In other words, our range is y is greater than or equal to 0. Now we're going to apply transformations to figure out the new domain and range. So using the same transformation rules from all of the lessons, inside affects the x values but in the opposite way. So I see x plus 1 on the inside of the radical, so that means we're really going to do x minus 1. The outside values affect y and in the same way, so I have this -2 out here connected by multiplication and the plus 3. So we're going to do y times -2 plus 3. Now we just have to apply those to our original domain and range. So the domain of this function, if I apply my rule of subtracting 1 from my x values, I'll get the domain is x is greater than or equal to -1, since 0 minus 1 is -1. Then if we apply our y rule to this, our y rule is to take our y values, multiply by -2, and then add 3. So as I do this, we're going to multiply 0 by -2, giving us 0, and then plus 3 will give us 3. However, anytime we work with inequalities and multiplying or dividing by a negative, we're going to have to switch the inequality sign to preserve the inequality. Since we're multiplying by -2, we know the graph is going to be reflected, meaning the graph is flipped, so we need to flip the inequality sign to match that. So here is the domain and range of this transformed function f of x. In this example, we're going to be graphing the equation f of x equals -2 times the square root of x plus 1, and then on the outside we have the plus 3. So applying the same rules, transformation rules, inside x opposite, so I see x plus 1, means I'm going to be doing x minus 1. In the outside numbers, we have the times -2 and then plus 3. So I'm going to do y times -2 and then plus 3. Now I know the original function, the square root of x, its starting point is at 0, 0, and I know it goes through 1, 1, and I also know it goes through 4, 2. So I'm going to apply the transformation rules to these 3 points to get my new transformed function. 0, 0, though, mind you, is the starting point, so as we graph, we are going to start at 0, 0, and then curve through the other 2 points off the side. So what is the transformations. We're going to subtract -1 from x, so 0 minus 1 is -1, 1 minus 1 is 0, and 4 minus 1 is 3. That is not a 3. There we go. And then for the y transformations, we're multiplying by -2 and then adding 3. 0 times -2 is 0, plus 3 is 3. 1 times -2 is -2, plus 3 is 1. And 2 times -2 is -4, plus 3 is -1. So I'm going to plot my 3 points, and I'm going to make sure I keep track of this point here, -1, 3. And my other 2 points are 0, 1, and 3, -1. I can tell that the graph's been reflected because it's been multiplied by a negative. And as I go through and try to draw this in, I need to start at the point that was originally 0, 0, which is now -1, 3. So I'm going to start at that point and then curve through the other 2 points off the side of the graph best I can. So it's going to look something like that. Okay, in this example, we're going to be graphing the function f of x equals the cube root of the difference of x and 2, and then -1 there on the outside of the cube root. So starting off, get the transformation rules. Inside x opposite, I see x minus 2, which means we're going to do x plus 2. Outside of x, the y value is in the same way, so there's only one number connected on the outside. Remember, the cube root, the index, just tells us what type of function it is, the basic shape, and the basic characteristics. So the only number outside that's going to affect the y values is the -1. From there, I'm going to take out the original cube root function information, or just some points that I can use to reference on the cube root function, which are -1, -1, 0, 0, and 1, 1. Just like with other functions, I'll apply the transformations to these 3 points. Applying my x rule, we'll add 2 to each of my x values, giving me 1, 2, and 3. And applying my y rule of y minus 1 to each of my y values, -1 minus 1, -2, 0 minus 1 is -1, and 1 minus 1 is 0. Then if I go and plot those points, we have 1, -2, we have 2, -1, and we have 3, 0. The basic shape kind of looks like a stretched out S. Wow, that was horrible. It kind of looks like a stretched out S for the cube root function, so I'm going to try to draw that in as best as I can. I always have trouble drawing this particular function the best as I can here. Yeah, kind of like that. But there we go. That is the cube root of the difference of x and 2, and then -1 there on the outside. Okay, in this example, we're going to be describing transformations on the function f of x to form, there's an m missing, the function g of x equals 5 times the square root of the sum of x and 2, and then -3 on the outside. So to do this, I'm going to pull the transformation rules out first. So the inside affects the x values in the opposite way. Since it says x plus 2, that means what's really going to happen is we're going to take x and subtract 2. The outside affects y and in the same way, so we have 2 things on the outside. So we're going to be multiplying y values by 5 and then subtracting 3. To describe it, I'm going to start with multiplication and division. So multiplication and division here, it creates a dilation or a reflection. Now it's a dilation if it changes the value of the number. If we multiply by 5, the value of the number will be changed. So we do have a dilation. It is a vertical dilation, and to be precise, it's a stretch because we're multiplying by 5, a number greater than 1. So, and it's vertically, since it's affecting y values, by a factor of 5, because we're multiplying by 5. There's no reflection on this one because we're not multiplying by a negative. When you multiply by a negative, it changes the sign, which therefore creates a reflection. However, we do have addition and subtraction, which means we have a translation that we have to take care of. So we are translating left 2 and down 3, since we have addition and subtraction on both x and y. So in this example, we're asked, how can we rewrite the radical function h of x, which is equal to the square root of 4x plus 16, with a plus 7 on the outside, to identify its transformations from the parent graph of f of x equals the square root of x. Now we could try to describe the transformations as is, however that gets a little tricky when we try to describe the translations and dilations and stuff, whenever there's multiple things going on the inside of the function. So one of the ways we can deal with this is just rewrite it so that there's no coefficient on the inside. And for most types of functions that we've looked at throughout the year, we can do that with, or it's already done for us. So in this case though, we're going to look at how to actually do this. So if we have the square root of 4x plus 16 plus 7 on the outside, what we're going to do is we're going to look for factoring out a number between the two terms here. If we do that, we can see that 4 goes into both of the terms. So we will factor out 4, giving us x plus 4, with the plus 7 on the outside. Then, according to properties with radicals, since these two expressions, the 4 and the x plus 4, are connected by multiplication, we can separate them into their own radicals. So we have the square root of 4 times the square root of x plus 4. Of course, the plus 7 is coming down for the ride. And then the square root of 4 is 2, so we get 2 square roots of x plus 4 with the plus 7 afterwards. So h of x can be rewritten like this. To describe the transformations now that's been rewritten, we have inside stuff, which affects x in the opposite way. So x minus 4 is our rule. We have a times 2 on the outside and a plus 7 on the outside, so y times 2 plus 7. Continuing to describe the transformation, so I'm going to describe my dilation here. We're multiplying by a factor of 2, so it's dilated vertically and specifically stretched by a factor of 2. And then we also have addition and subtraction involved. So we are translating left 4 and up 7. Now I do have some side notes with this. Okay, side note number 1 is, first of all, you can describe the transformations for this function as is. However, a lot of times it can be difficult for the order since we don't do a lot of horizontal dilations or stretches and compressions. So if I go ahead and try to write out the rule as is, inside affects x in the opposite way, which means order of operations happens in reverse as well. So what would be happening here is we would take our x values, we would subtract 16, so it appears like it's shifting 16 to the left, and then we would divide by 4. If I break that down farther, it would be x divided by 4 minus 16 divided by 4, which is 4. And then for the y rule, it would just be y plus 7, because only plus 7 is outside if we're going at it at this approach. So as far as describing the translations, we would have a horizontal compression, since we're dividing by 4 as the rule, which is a type of dilation, by a factor of 4. And we'd also have translations left 4, and up 7. Okay, the second note I want to make is about rewriting the expression. We can still rewrite the expression the square root of 4x plus 16 for any radical function, even if it's not a perfect square, barring that imaginary numbers wouldn't really be coming into play here. If we had that case, for example, if we had the square root of 3x plus 12 instead, we can still factor the 3 out, factor whatever that leading coefficient is out, giving us x plus 4, and separate it into the two radicals, square root of 3 times the square root of x plus 4. Unfortunately, since this is not a perfect square, it can't be simplified farther, which means if we were to try to describe the transformations of this, it would be a vertical dilation. Again, in this case, a stretch by a factor of the square root of 3, which isn't pretty, but it still is a description of the transformations that is valid. So regardless of what number here sits here with x, we can still rewrite it as a vertical dilation rather than a horizontal dilation, which is much more customary to do. The only number we can't rewrite is if x is a negative coefficient. We can't completely rewrite that, which would create a horizontal reflection. In other words, a reflection across the y-axis, which will happen in the last example here. Okay, in this example, we're going to be graphing the equation f of x equals the square root of the difference of x, or 2 and x, and then minus 1 on the outside. If I were to try to rewrite it like in the previous problem, to gauge the transformations without having a coefficient here beside x, I'd rewrite it as negative x plus 2, and I would try to factor out negative 1, giving me x minus 2. In factoring out negative 1, I would try to break apart the radical, giving me negative 1 times the square root of x minus 2, and of course bringing down my minus 1 on the outside the entire time. But we get to this point where we see we have the square root of negative 1. So in this case, it's not very effective to try to rewrite this because, well, I really can't. So instead, I'm just going to work with the original function and go off the transformations based from there. So if I try to get my transformation rules, the inside affects x in the opposite way. So I see x, or 2 minus x, which means I am taking x values and I'm adding 2. So I need to subtract 2. And then I am also multiplying my x by negative 1. So I will divide by negative 1. Sometimes it helps to rewrite it as negative x plus 2. Makes it a little easier to see how things are connected. Remember that since it's inside, the order of operations is in the opposite way as well. I can simplify this rule a little bit by just dividing both terms by negative 1, meaning I'm going to have negative x plus 2 instead. And then for the outside rule, I'm going to take my outside stuff, which will affect y values, in the same way. So I just have a y minus 1, since there's only a subtracting 1 on the outside. Now the key points, the reference points that we use for the square root function were 0, 0, where it kind of starts, 1, 1, and then the next perfect square, 4, and its square root, 2. If I apply my transformations, my first transformation for x is to multiply by negative 1 in the simplified version, multiply by negative 1, and then add 2. So 0 times negative 1 is 0, plus 2 is 2. 1 times negative 1 is negative 1, plus 2 is 1. And then 4 times negative 1 is negative 4, plus 2 is negative 2. Now I'm going to go back and apply my y rule, which is just subtracting 1. 0 minus 1 is negative 1. 1 minus 1 is 0, and 2 minus 1 is 1. Now I'll go ahead and plot the points, my reference points here. We got 2, -1, we got 1, 0, and we got the point -2, 1. 0, 0 was my initial point, which has now become 2, -1. So that's this point right here. I need to start at that point and then curve through the other points off the side of the graph. I do know because I was multiplying or dividing by a -1 on the inside, it has a horizontal reflection, which means it flipped from side to side. So it's going to be going off to the side, curving through both my points, something like that.